Exponential and logarithmic equations. This video will help you use like bases to solve exponential equations, use logarithms to solve exponential equations, write the exponential form of a logarithm to solve a logarithmic equation, use the one-to-one property of logarithms to solve logarithmic equations. Using like bases to solve exponential equations. So we're going to use this basic idea here, and it's a pretty simple idea, is that if I have two things equal to one another here, where the bases are the same, if b to the m power and b to the n power are equal, then that tells us that m is equal to n. So that's a pretty straightforward idea, and so all we do is we do a little manipulation. We use some algebra to rewrite the equation in this form. And then, so we want to make sure when we write it in this form that we have the same basis. And so that's going to kind of be the little trick to this. Not too difficult, but that'll be the trick. Get the same basis. Then once we know that, then we know the two exponents are the same. And then we can solve for the variable. So this gives us our first form of solving for a variable that's in the exponent. All right, notice when we have a variable up here in the exponent, it's a lot trickier to solve for that than it is if the variable is down, like in terms of maybe something added on one side or multiplied or divided or something like that. Had a lot of practice solving those. Those are pretty easy to solve. Solving for when the variable's in the exponent's a little bit trickier, and this will be our first strategy. All right, so let me take a look at an example now. So we're asked to solve this guy right here. 5 to the 3x minus 6 power is equal to 125. Now, one thing we could do is we could use guess and check up there for variable x and pick a value, find a value that gives us 125. You know, we also probably could just say, hey, I know that 5 to the third power, if I take 5 here to the third power, it gives me 125, so I could figure out then that 3x minus 6 equals 3. I could solve that. That would work here, but as things start to get more complicated, like this practice problem over here, it's going to be a little bit trickier to do that. So let's take a look at the solution process here. So what we want to do is we want to rewrite this 125 as a base of 5 to some power. And so I say, okay, well, 5 to the third power, that gives me 125. Now, once I have my two bases the same, 5 to some power is equal to 5 to some power, then I can say those two exponents then have to be the same. And now we get this pretty straightforward linear equation to solve. 3x minus 6 equals 3. We go ahead and solve that, and we find that x is 3. Okay? If we plug that back up in here, we could see 3 times 3 would be 9. 9 minus 6 would be the third power. And so 5 to the third power would, in fact, equal 125. All right, so now we're going to have to do the same thing. I'm going to have you practice this one. I'm going to have you pause your video player and practice this one. So notice we're not going to be able to write 8 to the fourth 4 to some power here, but I think we can go even further. I think we're going to want to write this as 2 to a power and write this as 2 to a power. And then also remember this, that if I have x to the b and then I raise that to another power, like maybe a, that power to a power in our exponent rule is x to the ba. So we'll have to use that idea here as you're solving this. So go ahead and pause your video player now and give this a shot. What we're looking for here is an answer of negative 12. So if you work this out perfect here, you'll get an answer of negative 12. So go ahead and pause now and answer this question and hit play when you're done. All right, so taking a look at these two bases here, we won't be able to write this as 4 to some power gives us 8. So what we do then is we try to look for a smaller factor in there where we could match these things up. So I'm thinking, all right, 4 won't work, but perhaps 2 will. I could certainly write 4 as 2 to the second power, and I can write 8 as 2 to the third power. So that is the common base we're looking for here. So I'm going to write this as 2 to the third power raised to the x plus 2, and 2 to the second power raised to the x minus 3. All right, now I have this common base, 2 to the third power, 2 to the second power. I still have to do some manipulation here, because notice this base right now is 2 to the third, and this one is 2 to the second. So we still don't have the same base here. But what we're going to do is use this, what I mentioned earlier, is this exponent power rule. If I take a power raised to a power, I multiply those two together. And so that's what we want to do here. I want to take and multiply this 3 times the x plus 2. So this would be 3 times x plus 2. And over here, 2 times x minus 3. Now notice, once I do that, this is now my exponent up here. That's my exponent. That's my exponent. I now have the same base of 2. So now, since these two are going to be equal, I could say these two exponents now have to be equal. And let's see, let's distribute this as we go here. So I would distribute the 3 up there. That would be 3x plus 6 is equal to 2x minus 6. All right, let's see. Subtract 2x from both sides. And I'll get x plus 6 equals negative 6. Subtract 6 from both sides now, and I'll get x is equal to negative 12. All right, and let's check this out. So if I plug this guy back in up here, I would have 8. Negative 12 plus 2 would be to the negative 10th power, is then equal to 4 to the negative 12 minus 3. That'd be negative 15. 4 to the negative 15th power. And if we calculate that out, we will see that that checks. All right, let's take a look at our next case here. Now we're going to use logarithms to solve exponential equations. So what happened before, what was really nice in that last exponential equation, was that we could write each side of the equation using the same base. In that practice problem we did, we were able to write each side so it had a base of 2. Well, that's only a small number of equations where that could happen, where we could write each side to exactly the same base. So if that cannot happen, then what we do is we use logarithms to solve these exponential equations. So step 1 is to isolate the exponential expression, meaning we're going to get the thing to the exponent on one side all by itself. Once we do that, we can either take the natural log or the common log, either one. Usually we use the common log unless we're dealing with a value of e. If we're using a value of e, then we would take the natural log of both sides. And we're allowed to take the natural log or the common log of both sides of an equation, just like we're allowed to multiply or divide both sides of an equation. Okay? And then this is something that's really cool about logarithms. So remember, if we have an exponent in our logarithm, we can take that exponent and write it out front as a coefficient or multiplication. And what that allows us to do then is it allows us to transform now an exponential equation into an equation with no exponents, where the variable now, instead of an exponent, is just multiplication. And once we've written the variable as multiplication, we've had lots of experience solving for that variable. All right, let's take a look at an example now. Solving an exponential equation. So here's my example here. 5 to some power is 134. Well, I can't think of anything 5 to some power being 134. I could use guess and check for a long time to figure out what that x is, but it's much faster to use logarithms here. So we've already got my exponential term isolated, meaning it's all by itself on one side. Now I'm going to take either the log or the natural log here of both sides. And what that allows me to do then is now I can take that x, write it out front. X times the natural log of 5 is equal to the natural log of 134, and then divide both sides by the natural log of 5. And so these are just numbers, the natural log of 134, the natural log of 5. All we have to do then is plug this into our calculator, natural log of 134, leave it in there, divided by natural log of 5 to come up with our answer. One thing we don't want to do is round. There's no rounding here as we're doing this calculation. You want to leave this answer directly in your calculator, then divide it by the natural log of 5. And again here, we're not getting an exact answer. This is an approximation. This is the exact answer right there. But most of the time when we're doing calculations, we come up with an approximation. All right, so that's the idea here. Now I want you to go ahead and pause your video player now and answer this practice question. Let's talk about this practice question just a little bit. I think it's going to be very similar to the example I just showed you. We've got both exponential equations isolated here, so now we're ready to take either the natural log of both sides or the common log of both sides. And what that'll allow us to do then is pull this exponent here and here. It'll allow us to pull those exponents out front. once they come out front, we'll be able to solve. Now the algebra is a little bit tricky here, so be careful as you're solving this. All right, go ahead, pause your player and hit play when you get done to see how you did. All right, as discussed, everything's all isolated here, so I'll take the natural log or the common log, doesn't matter. Okay, and as discussed, that allows us now to pull those exponents down in front and turn them into multiplication. So let's see, I'll have 2x minus 1, I'll put that in parentheses, times the log of 3. And then over here, I'll have x plus 1 times the log of 4. All right, let's see here. We want to get x all by itself. So we're going to have to collect like terms here. So what I'm going to have to do first now is distribute this log of 3. And again, this is just a number. We're not going to calculate it yet, but this is a number. I'm just going to multiply that number here and here. Same thing with the log of 4. It's just a number. I'm going to multiply it there and there. So it's going to look like this. 2x times the log of 3. And I think putting the log of 3 in parentheses here will really help you keep track of what's going on here. And then minus a negative 1 times that will really just be minus log of 3. And let's put that in parentheses again still, because that's just a number. All right, on this side, I'll have x times the log of 4, and then plus the log of 4. Okay, so now what I want to do is I want to get all my x terms to one side and everything else to the other. So I think I'm going to subtract. All right, let's see, look at what we have now. This is really kind of confusing here, but let's write it out. 2x times the log of 3 minus x times the log of 4. And these are not bases there. I should have written that up a little bit, but log of 4 now is equal to log of 4 plus the log of 3. And again, these are all just values. It's going to be an approximated value there. All of those are just values. Now, this is kind of the tricky part here. We write this out. You might not know where to go at this point, especially right here when you're writing this stuff out. You're like, well, I don't know what's going on here. But you go ahead and just write it out here, exactly what we have. And now we really need to get x separated from these logs to kind of solve for it. You know, I could calculate what this is. I could calculate what that is and multiply it by 2 and subtract, but I'm not going to be very accurate there. What I want to do is I want to separate x out from those two terms, and I can, because notice we have a common factor of x in here that I could factor out front. And once I do that, now we're going to be able to solve our problem and get a nice accurate answer. Okay, because once I factor the x out front, now I can divide both sides by this to get x by itself. And so 2 log 3 minus log 4, that's going to be equal to x. And I'm going to erase this because I'm running out of room here. That's going to be equal to x. So now this is something that I can get a nice approximation for. So I'm going to punch that into my calculator. The way I'm going to do this is I'm going to put parentheses around these guys. I'm going to say this is log 4 plus log of 3, and then I'm going to divide it by this next set of parentheses so that I get this all in one calculation here, because I don't want to round as I'm doing this calculation. I'll lose my accuracy. All right, and so we put that guy in there and we calculate it out, and we get approximately 3.064. If I don't specify anywhere what to round to, just round to the tenths, hundredths. I did the thousandths here, but tenths or hundredths is fine. All right, so we just got done now solving exponential forms of equations. Now we're going to solve equations that have logarithms in themselves. All right, and one real nice thing to do, remember, we've already learned how to transition back and forth between the logarithmic form and the exponential form. Well, if we have something written in logarithmic form, one of the first things we check to do is to see if we can translate it back to an exponential form. And we've already learned how to solve the exponential form, so we can just go from there and use the skills that we just developed solving the exponential form. So first thing we want to do when we're solving logarithmic equations, if we're going to try this strategy here, is to get the logarithm all on one side. And again, once the logarithm is all on one side, now we can transition this back to the exponential form. And remember what I told you guys before, it's as easy as taking the base of the logarithm now becomes the base on the other side. And that's what you have right here. Okay? So we have right there. Once we rewrite this in exponential form, we go ahead and use our skills and solve the variable. Then again, we just want to check and make sure when we get done that our solutions are valid. So right here, m has to be greater than 0. It can't be 0, it can't be negative, because we can only take the logarithms of positive values. So we want to make sure and be careful and always check our solutions here. All right, let's take a look at an example, and then we'll have you try a practice. So we're asked to solve this logarithmic equation here. Log of base 2 of the x minus 4 is equal to 3. Now, one of the first steps to do is to get this logarithm, a single logarithm, on one side of the equation. Well, we already have that here. So the very first thing I'm going to do now is take the base of my logarithm, which is 2, swing it over here, and then I'll have this. 2 to the third power is equal to x minus 4. Now, that's a pretty easy equation to solve. 2 to the third power is 8, and then we add 4 to both sides. We get our solution is 12. Now, I just want to plug this thing back in and make sure it works. And really, all this essentially does is if you take these values and plug it back into the logarithms of your original equation, got to go all the way back to the original, we want to make sure that we end up with positive values there. So I'm going to look and say, hey, 12 minus 4, that's 8. I'm still positive. My solution is going to be good. Just to check even further, we can come back down here and say, hey, 12 minus 4 is 8. And then we could just check this real quick, bring this base over here. 2 to the third power, in fact, is 8. So this does check out. All right. Now I've given you a practice problem here. It's going to be a little bit trickier because notice you don't have it down to a single logarithm. So what we want to do first is we want to manipulate this side to get it down to a single logarithm. We've already practiced some properties of logs that allow us to condense this expression into a single logarithm. So that's the first step here. Once we condense it into a single logarithm, then we can go ahead and use the strategy I just gave you in the example. So go ahead now and pause your video player and give this a shot. When you're done, hit play to see how you did. All right, let's take a look. So remember, we can write the sum of logs as a product of a single log. So notice I have an addition sign in here, and I'm able now to write this as a product of those, a product of those two. So really, this is going to be log of the first x times x minus 3. That allows me to condense that into a single logarithm. Once it's a single logarithm, I can use the exact same strategy I did over here in the example. One difference here is notice there's no base written on this logarithm. That's because it's the common log. So it's understood that with the common log, our base here is 10. So I'm bringing this 10 over to the other side, and I'll have x times x minus 3 is equal to 10 to the first power. Well, 10 to the first power is just 10. So let's see, I'll distribute my x here, and I'll get x squared minus 3x is equal to 10. Well, now we've got a quadratic here, and so remember our strategy for solving a quadratic is get everything to one side, 0 on the other. So it's going to be x squared minus 3x minus 10 is equal to 0. Let's factor this guy out. Hopefully this will factor x and x. Let's see here. We've got plus and minus since my last term is negative, and I'm thinking minus 5 plus 2. Let's see, that would give me negative 10 and then a negative 3x for the middle. So my two potential solutions here are x equals negative 2 and x equals positive 5. Now I want to check these and make sure we're not going to blow these the original equation up here by getting a 0 or a negative in my logarithm. And sure enough, right away, if I tried this negative 2 up here, it's going to be the log of negative 2. So right away I know that one's not going to work. Let's take a look at 5. If I put a 5 in this statement up here, 5 minus 3 gives me a positive 2. That's fine. And then over here, log of just positive 5. That's also fine. So there, I know that is going to be my solution, just x equals 5. All right, so we just learned one strategy for solving when we have a logarithmic equation, which is to get the logarithm all by itself and then transition it to exponential form. All right, another way to do this is using the one-to-one property of logarithms to solve logarithmic equations. All right, and so one thing that we can do is if we've got this log and they both have the same base, notice they both have the same base of b, if this statement is true, then we can know, since the logarithm is one-to-one, meaning every input value matches to just one output, and because the logarithmic function is one-to-one, then we can say that if these two logs are equal to each other and they have the same base, then we know that m is equal to n. And what that allows us to do then is it drops the logarithms out of our equation. Once we drop the logarithms out of the equation, it's very easy to solve. So we go ahead and then use our algebra to solve our equation. And then just like last time, we want to make sure that we check our answers. All right, let's take a look at an example now, solving a logarithmic equation. So I've got my equation here, and it looks like quite a doozy. But you'll see that once we kind of start to condense some things here, it's going to get pretty easy to solve this. So in our rule, in our property, we had a single logarithm on each side. Well, we don't have a single logarithm over here on the right. So I'm going to use my skills, my properties of logarithms, to condense this. And remember, I can write subtraction as division, as a single log division. So I'm taking this subtraction here, and now I'm writing it as the first divided by the second in a single logarithm. Now, once I have this, I have the natural log of x minus 3 is equal to the natural log of this stuff. Then those two things have to be equal. So now I can say x minus 3 is equal to that stuff. Now it's just a matter of algebra. So the first thing I would do is I'd clear this x plus 1 out of the denominator. So I'd multiply both sides by x plus 1. I do that on this side, and I do that on this side. And so you can see me over here taking x plus 1 times x minus 3. Now on this side, the reason we multiplied is because those are going to divide out then. And it will give us just 7x minus 23 on the right side. And x minus 3 times x plus 1 on the left side. All right? Simplifying the left side, we multiply these two guys together. We get x squared minus 2x minus 3, and over here 7x minus 23. Now again, we recognize that we have a quadratic because we've got a squared here. So anytime we have a quadratic, we get everything to one side, 0 on the other. So moving some terms around here, we're going to get x squared minus 9x plus 20 is equal to 0. Factor that guy out, factors into x minus 5, x minus 4. So we've got two potential solutions here, a 5 and a 4. Now we want to check these back in the original equations and make sure we don't end up with 0 or anything negative. So let's see. Let's check 5 first. So we'll check 5 here. That's good. 5 plus 1 is 6, no problem. 5 here. Let's see. 5 times 7 would be 35. 35 minus 23, that's still positive. We're okay. And then here, 5 minus 3 would give us positive 2. So that solution works. All right. Let's check 4 the same way. 4 plus 1 is 5. No problem there. 7 times 4 is 28. 28 minus 23 is positive 5. Still positive. No problem. We're getting close here. 4 minus 3 gives us 1, but that's still positive. So we're good. So both of these solutions check out. And so we would say both of these are our answer. All right. Now it's time to do a practice problem like this. Very similar to the one I just did. We got to get them down to a single logarithm on each side. So you're going to have to do some work over here on the left first to condense that down to a single logarithm. Once you do, you'll have the natural log of one thing equals the natural log of the other thing. Therefore, those two things have to be equal. Since the logarithmic equations are one-to-one, those two things will have to be equal. And you go ahead and use algebra to solve the equation. So go ahead and pause your video player now and give this a shot. When you get done, hit play to see how you did. All right, let's see. We want to condense this into a single log. Subtraction can be rewritten as division as a single log and a quotient. So let's see. So it'll be x plus 2 divided by 4x plus 3. So I wrote a little too much in there. And then that's going to be equal to the natural log of 1 over x. All right. Now, since these two natural logs are equal, these two algebraic expressions are also going to be equal. So I think we want to clear everything out of this equation. So I'm thinking about just multiplying by my denominators here. So I'm going to multiply by x. That would clear this guy out here. And then I'm going to multiply by 4 plus x, or sorry, 4x plus 3. That will clear all of the factors out of my denominator here. So let's see, I multiply by the first one. Notice the 4x plus 3 will divide out. So the 4x plus 3 will divide out, and I'll have left with x times x plus 2. When I go to multiply by my other term here, the x's will divide out and leave me with 1 times 4x plus 3. So that's just going to be 4x plus 3. All right, getting closer here. Distribute my x. I'll have x squared plus 2x equals 4x plus 3. It's a quadratic. I've got a squared, so let's get everything to the left side here. So I'll minus 4x minus 3 from each side. Let's see, and then I'll have x squared, minus 2x minus 3 is equal to 0. Let's come around up over here. Now we'll factor this. Let's see, x, last term's negative, so I need plus and minus. Let's see, 3, so 3 and 1, and I want more negatives than positives, so I'm going to put the 3 there and the 1 there. And let's see, so my first potential solution is x equals negative 1. My second potential solution is x equals positive 3. Let's check these guys back. Let's see, when I check negative 1 into that guy right there, I run into a problem. Notice 1 divided by negative 1 is a negative value. I won't be able to take the natural log of a negative value, so that one doesn't work. Let's check 3. So there I take the natural log of 1/3. That's no problem. Here it's going to be positive because it's going to be 12 plus 3 will be 15. It's no problem there. Check here. 3 plus 2 is 5, so that one's good. So my solution here is just going to be x equals 3. All right, let's take a look now at example 5, which is an application. And so this is very common for a use of logarithms, is we're solving for an exponent here. So let's take a look at this equation, and you can see how we can use logarithms to solve for an exponent. So how long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? So we're using our compound interest rate formula. This is the amount of the account after maturity, after the period of time. That's the amount of monies in the account. P is our principal investment, which in this case is $3,600. 1 is just 1. R is our interest rate, which is 8%, but we would want to write 8% as a decimal. So you can see me writing that as 0.08 here. N is the number of times it gets compounded in a period. Well, a period here is a year, because that's what the interest rate was. It's compounded quarterly. That means 4 times a year. So N would be 4. And then up here, 4 right there again. This N and this N are the same. So 4 goes there. And what we're trying to solve for is here is the T for time. We want to know how long it's going to take this $1,000 to grow into $3,600. So let's see. First thing I'd do is I'd simplify this to get 0.102. At this point, we want to isolate our exponent, so I'm going to divide both sides by 1,000. And I get this statement here. 3.6 is equal to 1.02 times 4 to the t. Now, we're trying to solve for an exponent here. That's hard to do. With these bases, we will not be able to get these bases the same, so we're either going to use the natural log or log base 10 here, but we're going to take the log of both sides. In this case, I've taken the natural log of both sides, and what that allows me to do then is take this exponent, bring it out front, turn it into multiplication. Now the natural log of 1.2 and the natural log of 3.6 are just numbers, so I'm just dividing both sides by the natural log of 1.02 and 4, and you can see when I do that division, I get approximately 16.2 years. So that's a very common sort of application we use logarithms for, is when we're solving for an exponent in real world problems where our bases and our numbers are not real nice and clean.